Hi, my name is Johnathan Scott. The title of my project is the process redesign for the reduction of wall thickness variation within thermoformed components. The company I'm working with is Aero Services Pty Ltd, and my faculty advisor is Professor Dan Waldorf. This is the agenda I'm hoping to cover today, and it should take approximately 10 minutes. Aero Services is a design and manufacturing organization based in Johannesburg, South Africa. Their main focus is on thermoforming thick-gauge plastic interior components. Thermoforming, in its simplest terms, is the heating of a plastic sheet, driving a mold up into that sheet, and then using a vacuum to suck the sheet over the mold, thus rendering the desired shape. There are two main types of thermoforming: thick-gauge thermoforming and thin-gauge thermoforming. An example of thick-gauge thermoforming is the dashboard of cars, and an example of thin-gauge thermoforming is disposable plastic cups. The process limitations are a depth of draw restriction, which is the height to width ratio, and its wildly varying wall thicknesses. We will see examples of these limitations later on. The problem statement for this project is Aero Services is looking to upgrade their thermoforming machines in order to decrease the amount of wall thickness variation innate to their process, thus improving the quality of their deep-drawn thermoformed parts. I did some background research and had a lot of communication with the operators, the CEO, and my faculty advisor. I also drew upon my experiences gained from 3 internships at Aero Services, where I was afforded the opportunity of learning how to use the machines. Here is an example part which Aero Services formed with their current process. If you have some time, pause the video and you'll notice that the part is far thicker at the top than it is on the sides. The root cause of this is that when the hot sheet first contacts the cold mold, the sheet begins to cool, and then it begins to solidify, and the remaining parts of the sheet will then stretch and thin to make up the sides of the part. A solution to this problem is to enable a pre-stretching ability on Aero Services' current thermoforming machines. We would like to go from the current state of having the sheet sagging before it touches the mold to having the sheet pre-stretched into a dome shape which distributes the material evenly before it's formed. This is done in 2 ways, either with a pre-blow or a pre-suction. The pre-blow method uses heated air blowing up onto the plastic to form the bubble shape, whereas the pre-suction is having a negative pressure above the plastic to lift it up into the bubble or dome. Here are the design specifications comparing the 2 options. The 2 main deciding factors are maintenance and ease of fabrication. This is my design for the vacuum box. In an effort to make the design cost-effective, I designed it so that Aero Services could use materials that they already had on hand. I placed the paneling on the outside of the frame so that the paneling would be sucked onto the rigid frame once the box is depressurized. My design for the vacuum box. It's simple so that it can be easily fabricated, and in an effort to make the design cost-effective, I designed it so that Aero Services could use materials that they already had on hand. I placed the paneling on the outside of the steel frame so that the paneling would be sucked onto the rigid steel frame when the box is depressurized. This should be strong enough to hold up to 1 atmosphere. Here is my proposed machine setup using a pre-existing fixture with an inverted pneumatic actuator. The vacuum box is fixtured to the pneumatic actuator above where the clamping frame will come out of the oven. The flowchart on the left is the existing process, and on the right is the proposed process. Here is a video of the new process. Material all the way out, box on its way down. There we see the dome, and now the material's up and we applied the table vacuum.
Okay, lift it off.
parts were formed to get a good idea of how different geometries and shapes would react to the new process. Here are our results for part 1. The graph on the right shows an ANOVA test, which is testing the difference in standard deviations between the old process and the new. It is seen that there is less variation in wall thickness used in the new process. The picture on the left also shows visual improvement from the old to the new. This is a cross-section of our part, and we can see that there's been a clear reduction in wall thickness variation from the old process to the new. The results for part 2 show no significant difference in the wall thickness variation. This could be due to the fact that the part is shallow and thus its depth of draw has less effect on it. However, you can once again see that there are visual improvements on the part. Part 3 is very analogous to part 1, so we won't really look at it much further. And finally, the economic analysis. Here is our projected savings in material costs using the new process, since the use of a pre-stretching method requires less forming material. A decrease in the material blank size of 8% is all that is needed to make this new process economically viable. Here is a projected cost savings using estimated scrap rates obtained from error services, since they have no data available. There is a projected savings of almost $5,000. And if we are conservative with this, we can divide it by 5 or 10. And even if we do that, this process still seems to be economically viable. I can conclude that the vacuum box worked and improved the process. And a lot of positive feedback was received from aero services. And I really learned a lot. How can we improve this process? Well, the addition of a vacuum regulator to control the bubble height will help control the reproducibility of the process. And not only will we control the variation in wall thickness within the part, but we will be able to control the wall thickness variation from part to part. Also, a box that could fit on multiple frame sizes would eliminate some of the fabrication costs and also the design costs associated with making multiple boxes for different projects. I would like to thank you for listening to my presentation, and I look forward to presenting to you in person.